Swayam Prabha. Digital India. Educated India.
Hello students. In our last class we discussed the first few experiments that classical mechanics could not explain and how quantum mechanics or some new ideas were necessary to explain those experiments. In our discussion we talked about the black body radiation, how Max Planck could resolve the problem in black body radiation or resolve the problem of ultraviolet catastrophe by assuming that the black body oscillators cannot have continuous energy, rather their energies are quantized, and how energy of these oscillators were proportional to the frequency of the radiation that were emitting. And in the second experiment of photoelectric effect, we discussed how Einstein could resolve the anomalies that were observed in photoelectric effect experiments vis-a-vis the existing knowledge in classical mechanics. Einstein had to suggest that the light, which we all know as a wave, also has a particle-like nature, and the energy of light is what he called as photon are the packets of energy, which is, and the energy of this packet was proportional to the frequency of the light, whereas the intensity of the light represented how many such packets or how many such photons are there in the source radiation. We will continue our discussion in yet another experimental results, where we would see that the existing knowledge in classical mechanics failed to explain the experimental observation and how new ideas were necessary to resolve the issue. The example that we are going to discuss today is the hydrogen atom emission spectra. If you look at the hydrogen atoms emission spectra as is shown here, you would see that the spectra shows several lines followed by some bands, and then there are some empty spaces, and then it gets repeated. For example, some more lines appear and then a band and some empty space and some more, and it continues. The emission spectra ranged between UV, visible and infrared range. We know from our previous classes that the emission spectra of hydrogen atom could be explained, or at least numerically explained by different spectroscopists, Lyman, Balmer, Paschen, Brackett and so on. So, therefore, we have this series of lines are called Lyman series, this is Balmer series, Paschen, Brackett and so on and so forth. And we also know that all these observations could be explained together by Rydberg by a single equation. However, these explanations lacked a fundamental understanding of the problem. They could reproduce the experimental observation as a merely numerical exercise, but we did not learn anything new about the system. So, this particular problem was taken up by Niels Bohr, and Bohr proposed his Bohr's atomic model. In Bohr's atomic model, Bohr assumed a few things. First of all, he suggested that an electron in an atom goes around the nucleus in a fixed orbit of radius r. And the second assumption that he made is that the angular momentum of this orbiting electron, which is given by m v r, m is the mass of the electron, v is the speed at which it is orbiting, and r is the radius of this fixed orbit r. m v r, the angular momentum of this orbiting electron, is integer multiple of h by 2 pi, where h is again the Planck's constant 6.626 into 10 to the power minus 34 joule second. With these two assumptions, Niels Bohr did a few more exercises and then came to the conclusion that the radius r was proportional to n square, where again this n can be 1, 2, 3 and so on. So, these are the integral multiples. The radius of these fixed orbits r is proportional to n square, and the total energy of this of different radius or the different orbits is 1 over n square. So, these are the outcomes that came out by making these two assumptions. It is very important to discuss about this assumption, because you see that in black body radiation Max Planck suggested that the energy of the black body oscillators are quantized. In photoelectric effect, Einstein suggested that the energy of radiation, energy of light is quantized. Now, in this experiment, Niels Bohr is suggesting that the angular momentum of the orbiting electron is quantized. What it means? It says that the electron, when it orbits around the nucleus in an atom, it cannot occupy any radius, rather its radius is quantized, it has an independence. The electron, while orbiting the nucleus, cannot have any continuous value of angular momentum, rather it has discrete or quantized value of angular momentum. And similarly, the energy of the electron, when it is orbiting the nucleus, it cannot have any continuous value of energy, rather it has got some discrete value of energy or quantized values of energy. So, this principle of quantization or the dependence of physical observables like radius, angular momentum, energy, their dependence on n, the integers, is coming out from one after another experiment. So, when we look at this, that the energy levels of hydrogen atom are quantized, then we see that this is where this is the energy level that comes out of Bohr's atomic model. We see that there are different energy levels, and the electron jumps from one higher energy level to a lower energy level and emits that radiation, and that radiation is what we see in the hydrogen atom's emission spectra. This model could explain why we have some lines, well separated lines, followed by some bands and then some empty spaces, because this model clearly shows that since the energy of the orbiting electron is quantized. So, therefore, from one orbit to another orbit, when the electron makes a jump, the energy that comes out of this process is also quantized. You cannot expect all possible energy values to be emitted by the hydrogen atom's electron. Rather, you are expecting, based on these laws, you are expecting that only certain values of energy are going to be observed, and this is what is being observed in this hydrogen atom's emission spectrum. Bohr's atomic model could explain the hydrogen atom's emission spectrum very well. However, it could not explain a few other things, few other related things. For example, the emission spectra of all heavier atoms could not be explained by Bohr's atomic model. Not only that, even for hydrogen atom's emission spectra, if you subject the hydrogen atom to external electric field or magnetic field, the Bohr's model could not explain the emission spectra of hydrogen atom in the presence of external electric and magnetic field. Because you would see in our next discussion that the two assumptions that here Bohr has made in his Bohr's atomic model have some flaws, and we will discover that what are these flaws, and then we will be able to tell why Bohr's atomic model could not explain the emission spectra of heavier elements as well as hydrogen atom's emission spectra in the presence of electric and magnetic field. But before that, we would discuss not another experiment, rather another theoretical idea that changed our understanding of physics forever. This was proposed by a young physicist, de Broglie. while explaining photoelectric effect experiments, Einstein suggested that light, which we all know as a wave, has got particle like nature. Now, de Broglie's hypothesis suggests that any particle that we see, that we observe, has got a wave like nature. So, Einstein suggested that light, which is a wave, has particle like nature. Now, de Broglie is suggesting the other way around, that all particles have wave like properties. So, if the particles that we know, that we can see in our macroscopic world, have wave like properties, then what are their wavelengths? So, de Broglie had an answer to that. De Broglie suggested that a particle with mass m and moving in a speed of v, or that means which has got a momentum of p, is associated with a wavelength lambda, which is given by lambda is h divided by p, where p is the momentum of this particle, and we can also write h by m v, where mass is m is the mass of the particle and v is its speed of velocity. Now, again one more thing that you must be noticing is that h, the Planck's constant, again appears in de Broglie's hypothesis. So, this was rather perplexing for many reasons, because we always knew that it was very hard for us to imagine that the everyday objects that we see, for example, a pen or a book which has a fixed mass or moving at a particular speed v, would be actually not a particle, but which is of course a particle, but also has got a wave like nature. But this is not hard to imagine or hard to understand, because when you look at this particular equation, you see that the wavelength of this particle is inversely proportional to the mass of the particle. The everyday macroscopic object that we deal with or that we encounter have got very high mass. So, since they have got very high mass, the de Broglie wavelength lambda corresponding to these objects are very small. So, therefore, even if they have wave like property, for all practical purposes, those wave like properties are not observable, or we are not able to observe them. However, when you go to microscopic world, when you talk about subatomic particles like electrons, where mass is very small, in that case the de Broglie's wavelength becomes considerably large. So, therefore, in such microscopic particles, you cannot ignore the wave like nature of the particle. So, Einstein suggested that light, which is a wave, which was well known as wave, has particle like nature, and now de Broglie is suggesting that, for example, electron, which was known to be a particle, has got wave like nature. Now, this brings forth to what is called as wave particle duality, that a particle can behave like a wave and a wave can behave like a particle. This wave particle duality leads to further interesting ideas, but one more interesting thing that comes out of de Broglie's hypothesis is that it provides a support to Bohr's atomic model, or the assumption that Niels Bohr made in his atomic model. This we will discuss next. For example, if you remember, Niels Bohr assumed that the angular momentum of the orbiting electron is quantized. MVR he suggested was equal to NH divided by 2 pi. Now, let us look. Suppose this is an electron which is going around the nucleus in a fixed orbit of radius r. Since this electron has a particular mass m, it has got an associated de Broglie wavelength. If this wavelength of this de Broglie wavelength of this electron is something that can fit the perimeter of the Bohr's orbit that it is orbiting, then you can see that no matter how many times it orbits this goes around this orbit, there will be a constructive interference. That means there will be always an in phase and the system would be stable. But suppose if the perimeter of the orbit does not match with the wavelength of the electron, the de Broglie wavelength of the electron, in that case you would see actually an out of phase. So, once there is an out of phase in the system, you would see there will be a destructive interference and the system will collapse. So, what it suggests is that for an electron to be stable in a fixed orbit, it should have a de Broglie wavelength such that an integer number of lambdas, the de Broglie wavelength, will fit the perimeter of this the circle, that is 2 pi r. So, now we also know, so lambda is our h by mv, is 2 pi r, and then we can rearrange this equation mvr equals nh divided by 2 pi, and this gives a justification to Bohr's assumption that the angular momentum of the orbiting electron is quantized. So, de Broglie's hypothesis that the electron has a particular which has a particular mass and moving with a particular speed has got a de Broglie wavelength, and this de Broglie wavelength has to be such that n lambda equals 2 pi r, and then only the electron will be stable in that orbiting nucleus, otherwise it will develop an out of phase and this is the electron would never exist. So, if the electron is orbiting around around the nucleus in a fixed orbit, then it must satisfy that the angular momentum of this orbiting electron is quantized. Now, as I have already mentioned that we have now come to a stage where we have this so called wave particle duality. Now, the particle behaves like a wave and the wave behaves like a particle. This gives rise to an interesting problem. Suppose I would I want to determine the position of an electron with an accuracy of, let us say, delta x. I want to see that whether an electron which has a particular mass, whether it is present within this range of space delta x. To do that, what experiment can I do? The one possible experiment is that I will allow electromagnetic radiation or light to interact with the electron, or I will shine light onto the electron and then look at the response. Now, if I want to determine the position of this electron with a precision of delta x, so I must use a light of wavelength lambda which should be less than delta x. Now, if I want to determine the position of the electron precisely, my delta x should be as small as I can get. So, if delta x is small, to be able to make that precise measurement, my lambda of the incident radiation should be even smaller. But I know if the radiation has got wavelength of lambda, it has got very and the lambda is very small. For small lambda, I have got extremely high momentum, because remember the wave has a particle nature. So, the light that I am sending has, if it has very low wavelength, then it has got very high momentum, and the moment this light interacts with the matter or the electron, since light is now a particle, the electron is also a particle, then there is a collision, and in this collision there will be momentum transfer from light to electron, because remember this light has low wavelength, so therefore high momentum. Now, the large momentum that this light carries will be passed on to the electron. So, the very act of measurement through which I interact the light with electron, the very act of measurement of the position of electron influences the momentum of the electron. How? Because the collision of light and electron will lead to transfer of momentum from light to electron, and therefore, electron's momentum will change. So, that means if I want to measure the position of the electron precisely, I have to give up my hope in determining the momentum of the electron, because the very act of measuring the position will compromise the result that I am getting out of regarding the momentum of the electron. Now, how do I resolve it? Of course, if I do not want to disturb the momentum of the electron very much, one easy way is to give what? If they send the light which has low momentum. So, if I have small momentum, then the collision will lead to minimal transfer of momentum from light to electron. So, therefore, the electron's momentum will not change. Now, if I have to prepare a light, or if you have to choose a light which has low momentum, small momentum, then I know that if p is small, then lambda is large. So, that means I have to choose a light source which has very large wavelength. Now, if I have chosen a very large wavelength, so the lambda, the wavelength must be less than the precision of my position experiment. So, if lambda is less, so that lambda is more, then delta x is even more, is even larger. So, in that case what happens, that my precision of position measurement is getting compromised. So, that means if I want to measure the momentum of the electron precisely, I will have to give up my hopes in making the position measurement exact. So, I can choose whether I want to measure the position of the moment precisely, position of the electron precisely, or whether I want to measure the momentum of the electron precisely. I cannot do both. So, there is this inherent uncertainty in measurement. So, Heisenberg proposed this relation that delta x into delta px, this is the uncertainty in the measurement of position, this is the uncertainty in the measurement of momentum, has to be greater than or equal to h bar by 2, where h bar is simply h divided by 2 pi. So, this is the idea about Heisenberg's uncertainty principle, that I can either measure the position or I can measure the momentum precisely, and not both. Now, we are well equipped to look at Niels Bohr's atomic model and what is one flaw that exists in that atomic model. If you remember, Bohr's atomic model said that the electrons go around in fixed orbit of radius r. So, that means Bohr assumed that he knows the precise value of r, therefore, the position of the electron. In the second assumption, he said that angular momentum of the particle is quantized, mvr equals nh bar. So, therefore, in two assumptions what he did is that he said that I know the exact position of the electron as well as exact momentum of the electron, and that is a strict no in quantum mechanics, because you cannot have precise knowledge about the position as well as the momentum of the particle, and that is the mistake in Bohr's atomic model, which prevented the atomic model to be used in case of heavier elements, and also to be able to explain the emission spectra of hydrogen atom in the presence of electric field and magnetic field. But when we consider the Heisenberg's uncertainty principle into our picture and have a real look at the problem, then in future class we would show that we can explain both the experimental results of the emission spectra of heavier elements as well as the experimental spectra of hydrogen atom in electric and in magnetic field. These are some of the key experimental and theoretical ideas that forced us to think that perhaps our understanding of the physical world is not complete, and we lack some key features from our discussion. And all these experimental and theoretical developments suggested that there exists a hidden world, the world of quantum mechanics, that is necessary for us to explore. Next, we would look at some of the key milestones in the journey of quantum chemistry. So far, what we have discussed is that some of the experiments that could not be explained through classical physics, and we needed some new ideas such as quantization of energy, quantization of radius, quantization of angular momentum. Then we also had duality, wave particle duality. The particles can have wave like nature, the waves can have particle like nature. All these new, interesting and unprecedented ideas were used to describe some of the these experiments. I would just take you through some of the important milestones in the journey of quantum chemistry and how it has become so relevant in today's research in physics and in chemistry. For example, to begin with, 1926 Schrödinger solved the hydrogen atom problem, and soon after Hitler and London provided an explanation as to of any chemical bond or the bonding in the smallest possible system, hydrogen molecule. So, we cannot actually describe a chemical bond, or we cannot talk about a chemical bond with complete knowledge unless we invoke the principles of quantum mechanics. The journey continued by Slater and Pauling, who showed how chemical bonding occurs in heavier molecules like nitrogen and oxygen. They introduced the concept of orbital hybridization, followed by soon after Kuhn, Mulliken and Slater, they proposed the molecular orbital theory, the concept of electron delocalization. Soon after, Hartree, Slater and Gaunt suggested this very useful self-consistent field and the variational principle for self-consistent field. In 1951, Ruthan provided a matrix formulation of Hartree-Fock theory that made this theory very popular, because around that time we are witnessing rapid progress in computers, and with the matrix formulation it was becoming easier for us to solve complex quantum mechanical problem through computers. Soon after Popel and Cohn and Schramm in 1960s and 70s put forward two very important theories, the wave functional theories and density functional theories, which are now two of the most commonly used quantum chemical strategies to deal with molecular system, large molecular system. And in 70s, Worcel and Leavitt took quantum mechanics to an even further height by introducing quantum mechanics to in the field of biology. Many of these names that I uttered in this lecture today have received Nobel Prizes for their seminal contribution, and in the rest of the course we would actually discuss more about quantum mechanics. As you have seen that there are many new ideas that have been put forwarded through in quantum mechanics, and quantum mechanics has become a kind of a new language. As in any new language, when you want to speak that language, when you want to communicate in that language, you must know the grammar of it. And in next few classes, what we will do is that we will discuss about this grammar of this new language of quantum mechanics. Thank you very much.